So the next presenters are from Spicy, which is a healthcare analytics company or something like that. And yeah, they will talk about a real project which they implemented, and actually the first half of the presentation will be held by Nora, and Nora will be generally introduce the project, I think, and the second half of the presentation is held by Valer, and Valer will talk about the technical details and the LSTM-based autoencoders, I think. So, and one more thing before they start, just to mention again that I'm looking for the next presenters. I always tell this you guys, and please don't be shy, because you know it's easy to stand here, just talk about the topics you work on, and that's all. So why not present? So really, I'm looking for somebody or multiple people, let's say, for the November meetup. I really want to do it in November again. So yeah, please just write me a private message, or just let's talk about it after the presentations. Okay. Okay. So Nora, please.
Okay, so welcome everyone, and thanks for coming, and also thanks Miklós for organizing this event. As you mentioned, we will talk about a real use case. We will show you a real use case. I will give you a short introduction about our company, and I will give you a really short description about this project in theory, and after that Valer will show you the tech details and also some source code. So that will be it. So about us, we are at Spicy Analytics. It's a 100% Hungarian tech startup company, or we are in the field of healthcare and pharma. We mainly do data analysis. Our motto is data science for life science. And we also have software developments. I think you can read that through. It's not that interesting for now. So this project that we will talk about, we call it Arrhythmia project. It's a research and development project since 2017, and we are working together with Dr. Jörg Lippert from Bayer Berlin. So special thanks for Jörg also. Our goal is patient clustering and progression among arrhythmia patients. So you can see this ICD code in Hungarian that stands for BNO code. So it's an international classification of diseases. Arrhythmia has ICD code I48. So we got our data from insurance, the national insurance company called NEOC, former known as OEP. So in Hungary, we have a pretty good situation with healthcare data. From NEOC, we can get all the patient records. So all of us have patient records stored at NEOC databases. We have problem with that if you go to a private clinic, to say so, for a CT or an MRI, that doesn't show in this NEOC data. So only the national institutionalized patients are shown there. So there are approximately 10 million patient records, from which around 5 million hospital care records, from which we are using around 200,000 to 500,000, depending on the ICDs, ATCs. ATC code stands for when you purchase a drug, that's called, it has an ATC code. So what was the first two steps when we got this request to analyze arrhythmia patients? we needed to classify patients before and after the diagnosis. So for that, we selected a 0.1 year in our time series data and identified the newly diagnosed patients during this year based on I48 ICD, which I mentioned you earlier. In the rest of the analysis, we will focus only on these newly diagnosed patients and examining their healthcare data 2 years before and after the diagnosis was given to them. So, as for step 3, for the progression analysis, we selected the newly diagnosed I48 patients year by year from 2010 to 2016 and followed these patients. Main topics were, for example, complications, hospital admissions, other ICD codes, therapy course, compliances, length of therapy, and so on and so on. So it's a really wide project, and as I mentioned, it's a research and development project. So maybe there is a light in the tunnel now, as Valer will show you, but there is still a lot to go with it. So, and finally, step 4, we decided to cluster these patients. You know, clustering is hard because we have time series categorical data, and we try to find meaningful groups, but for this analysis, we should not have any preconceptions about the population. So our model is based on clustering the raw data, and our analysis highlights associations in the data set. And from now on, I will give it to Valer, and he will come with the tech details and the source codes. Thank you.
So, basically about this project, arrhythmia is hard because arrhythmia is associated with every kind of other cardiovascular diseases. So, for example, stroke, but we can't find real causal relationships between these diseases. So, arrhythmia is associated with, for example, heavy smoking, or it could be associated with alcohol abuse, but we can't say for sure what causes arrhythmia or how it will cause other diseases. So, and to be even harder, our client requested that. I'm not a medical expert, I'm just a data analyst, but they requested us to do an analysis without any preconceptions. So basically, that's why we choose this method, because we tried to analyze the raw data and just rely on the machine to find associations. And they are trusting our results because we are not looking from a medical expert perspective on this data. Maybe we can find new associations or maybe just trivial associations, but in a further analysis those results can be verified or they can be classified only as artifacts, but that's the problem of a further analysis. So basically our method is a hypothesis generator. That's the idea. We're trying to find good or bad associations, but new associations. And that's why we choose the long short-term memory network and clustering. So yes, we talked about we have a patient. A patient has an arrhythmia record at some point in a time, and we are looking at her or his, all of her or his records before 1 year of this diagnosis. And we place each record into monthly bins. So basically we get a binary description for every 12 months before the arrhythmia diagnosis. And for example, we have, if they had a flu in January, or they had a stroke in March. Yeah, that's the that's our pre-processing, which is very simple at this stage. Instead of the binary pre-processing, we are thinking about, for example, using natural language ideas. What if we would use, for example, embedding vectors for the diseases? Or we could use a simple TF, term frequency, inverse document frequency representation. But that's all up now, because we only can validate these representations by having these clusters and looking back if they are successful representations. So yeah, and another thing, we can use recurrent neural networks to process this data, but we don't have any classification or regression goal. So that's why we are using autoencoders, and our idea, autoencoders, is for information extraction or information compression. So basically, if we transform this very noisy time series data, then maybe we can have meaningful vector representations for every patient, which can be clustered, and these will magnify the differences and the similarities of these patients, and maybe we can find meaningful groups. And yes, as the last step, we have our clustering algorithm, which is now a k-means, but I will talk about some developments and improvements which can be used on this data set. Yeah, so the basic idea has there are research about this topic. For example, I think this is one of the best implementation which can be reached or can be downloaded on GitHub. DeepCare, a deep dynamic memory model for predictive medicine. Yeah, you can see the idea. We have the history of the patients. They are working with embedding vectors for the disease codes, for the treatment codes, and any other patient data. They transform this data with a long short-term memory network, and they also use an attention layer. And another neural network will try to classify for the future risks. In this article, well, basically we took the lower part of this network, and we just created an autoencoder out of it. A remark about this: we try to model future risks too, but we realized that unfortunately, there are administrative reasons how NEAC codes these data. So it's very hard to decode this data as a time series data, or just decode the future risks, because the data is noisy. So there are many, for example, a patient can have many records about non-existing diseases. So for example, if I go to the doctor and they say, maybe you have arrhythmia, then I will have a record about arrhythmia. Then I will go to the hospital, they have an examination, and they say, maybe you have an arrhythmia. That's my second arrhythmia code. And then they realize, no, unfortunately, you don't have any problems. So I will get a U99 code, which means Cinnamorbo, so I'm healthy, and it was just an artifact. But I have two arrhythmia codes, so that's the basic reason for noise in the data set. So yeah, decoding the data is very hard. Future risk, to decode future risks is very hard, so that's why we started with an easier problem. With an autoencoder solution. So yes, our PyTorch implementation. Yes, so we use standard building blocks from the PyTorch library. Well, we have two channels in this example. We have the ICD encoder and the ATC decoder. The ICD codes are for the diseases, and the ATC codes are for the for the treatments, the drugs the patient used. So we use this decoder, and then we use a custom implemented attention layer for both LSTM networks, and then we use two hidden transform layers, which are simple linear layers, and then we use the decoder. So also, yes, I talked about how hard to decode the time dynamics, because, for example, it's hard. The example I mentioned, for example, I get a disease code, and then after I go to an examination. But sometimes I go on the next day if I have if I'm scared about, for example, arrhythmia. But maybe I'm saying that I feel well, so I will go only in the next month to the doctor. So this time dynamic can be very, very noisy because of the behavior of the patients. So we have another simplification in our autoencoder. We are just trying to recreate a binary representation of the pre-diagnosis period if the patient had that code or had that ICD code or ATC code. So we are using now simple linear layers in the decoder phase. Yeah, and it's basically the same as a multi-label classification. So we are using these binary cross entropy loss. Yeah. And yeah, so you can see the PyTorch's forward function, which uses the predefined layers. So we use the ICD and ATC encoder to transform the time series data. We apply the attention layer for both LSTM, and then we concatenate the two representations. We use the linear transforms, and we decode the data, and we return that. So about the attention layer, we use another article from natural language processing, especially from document classification, to implement this attention layer. And if you are not familiar with attention, it basically does that from an LSTM. If we have 12 months of data, we have 12 hidden representations. Then we use an attention vector which will multiply every hidden output of the layer, and then we apply on that vector multiplication output softmax layer, and that will choose for us the meaningful time moments of the input data. So this is for even LSTM networks can be it's called long short-term memory networks, but they can only focus at the end of the sequence. So basically we apply this attention layer to use all of our time series data to make a meaningful decoding process. Yes, and the clustering. So at the middle of the network, before the decoding phase, we have a vector representation after the training, and then we save every patient vector, and then we use the scikit-learn implementation of k-means over these vectors. About k-means, the hard question: how to choose the k parameter, how to find out the cluster size parameter. And this is from a pretty old article, I think from 2004, the stability-based validation of clustering solutions. So we have this algorithm, and we test the clusterings. We do all the clusterings from cluster size 2 to cluster size 15. We do each clustering, and we basically trying to split the data set into two halves, and we cluster one half, and then we teach a k-nearest neighbors classifier based on that half. And then we cluster the other half, and we try to predict the clusters, the predicted cluster labels from the first halves, halves k-neighbors classifier. And then we characterize how successful this clustering and prediction was. So we basically use the error rate between the two halves, and then we iterate this algorithm. We taking bootstrap samples from the data set, and then we will get for every cluster size a stability value. And the most stable clustering will be our chosen, will give our k parameter. So basically this idea is that if we iterate and do the clustering again and again, and if this will give us the same results, then that seems statistically that seems a stable, maybe a good clustering. But yeah. So yeah, about this code, we are taking from the representations our bootstrap sample, and then we choose the first half and the second half of the data set. We apply the k-means 2 times, and on the first half we teach the k-neighbors classifier, and then we use this custom implemented compare clusterings function, which will give for us the stability values. And yes, yeah, a hard thing about this comparison of clusterings, well, because k-means has a random factor, the algorithm, so it will predict different cluster labelings. So we need another trick with the Hungarian algorithm for bipartite graph matching algorithm to just find the two best matching cluster labels. And then after we found the best matching clusters, then those labels can be checked for the error rates, and that will be our cluster stability parameter. Yes, and for example, a plot, yeah, which shows us some problems. I will talk about that on the next slide. But the most stable clustering is with cluster size 2, and you can see it shows us an increasing function of error rates. So yeah, if we do on the representations, just for validation, we check visually the PCA and the TSNE plot. Then we only see a cloud. So yes, our algorithm seems to be a failure because we didn't find any clear distinct clusters. But I think it can be maybe a result, or we can maybe put more emphasis on developing these algorithms. But from our perspective, the result is that maybe we don't have clearly separated clusters. Maybe the arrhythmia patients are kind of a continuum. So basically, all the patients have the same cardiovascular problems. All the patients have the same comorbidities. All the patients get more or less the same treatments, but the difference is between the severity of the disease, and that's why we need the further validation. So, for example, looking at these clusters and with regression analysis, try to understand how, for example, these clusters have an influence, for example, on stroke prediction or any other diseases. Yes, and we had another idea to interpret the recurrent neural network. So in this article, you will find several methods for deep neural network interpretation. Just to mention some, for example, this method is sensitivity analysis, which basically does the same as backpropagation. Just we are not trying to backpropagate from the output to the weights of the network. We are trying to backpropagate to the input, and though where the highest where we have the highest squares of the gradient, that could be our most meaningful parts of the input, which really separates the data set. And this is one of the most basic methods. So we are now working on an interpretation. So for example, just to drop some names, layer-wise net, how is this called? I don't remember. That's a big shame, but if I remember, I will tell you. So yeah, we have another method. The method is basically about that, taking the output, just use the relevant parts. So for example, classification, the predicted label, and then we only use the positive parts of the activations of the neural network, and then we do transpose matrix multiplications from the activations, and we trying to from layer to layer backpropagate the meaningful parts of the prediction. So that's a more evolved way to do this kind of interpretational analysis. Yeah, and with this sensitivity analysis, which can be implemented with PyTorch's autograd.grad function, we just give the two input data and the output data, and then it automatically does the backpropagation. We take the square and we can create heat maps. So maybe the meaningful parts at the end of the year, and maybe there is some meaningful disease codes which influences the prediction, the creation of the hidden representation. And also for these are ATC codes, and yeah, in monthly beans. And maybe there are some drugs which has meaningful and strong influence on the network's output. Yes, so now we are developing these methods to validate these results if it's just a random artifact. My idea for now is bootstrapping the neural network and then check these sensitivity plots and then find out if it's a continuously appearing part of the heat map or it's just a random factor. Yeah, so in summary, deep learning has potential for exploratory analysis. These unsupervised methods, I think they are showing great promise, but they are very hard to do and very hard to validate our results because they can be messy. So these experiments, most of the time, I think they are open-ended research and development projects. There are no clear-cut, always working solutions to do this. And I think, especially in healthcare, we can't just trust in this plot as we don't do it. Further validation by classical methods are appropriate, and I think they are needed, especially in the medical in the medical area of data analysis, because doctors won't believe any our deep learning results. They always require regression analysis. And yes, I spoke about some potential developments. So instead of autoencoders, maybe there can be a variational autoencoder. There are several good research about how the latent space of variational autoencoders can be interpreted or can find meaningful parameters. Yeah, so that's maybe an evolvement. Or we could use more evolved clustering solutions like deep spectral clusterings, or even k-means could be further refined by gradient techniques. For example, in this Towards K-means Friendly Spaces article, there is a good example. Yeah, and layer-wise relevance propagation is the name for the method. So our other interpretation methods and definitely can be used and should be used, because sensitivity analysis is one of the most basic technique to do this. Yes, and thank you for your attention.
Okay, what are the questions, guys? Yes.
So, since you kind of said that the time series into a little bit window of 12 months, would it make sense to go for a very classical regression-based technique? So, not using LSTMs and all these memory networks, just to have an autoencoder based on like a feed folder or something. Did you consider that, or are there any arguments against it?
Yes, we did that analysis. We only used feed-forward autoencoders. The results were more or less the same, still with the same clustering solution. The cluster size 2 was the most stable clustering, and unfortunately we couldn't find any meaningful separation. So that's why we evolved this with a small step to a recurrent neural network, because maybe the time dynamics can be incorporated in that kind of way which separates these patients.
And on the other hand, like for the clustering mechanisms, you did any comparison to something like a DB scan or some kind of clustering methods whereby you don't define K, just try to figure out the density-based estimate and then see whether it confirms the K number 2 or
yes, we started those experiments. We are trying to evaluate those now. But I remember one of my colleagues looked at DB scan. I'm not sure about his results. We tried to create just some basic descriptor statistics about how the clusters separate. Yeah, we started that. I'm not sure about the results.
I have two questions. First is how significant is the attention layer for your results? So have you tried without attention, then you feel the urge to use the attention? Or can you do some feature engineering and replace it? If you have an experiment that area. Second question is, have you tried the model agnostic interpreter like Line or Shelby?
No. For yeah.
Which one?
Which one? About the second question.
Okay.
Yeah, I'm currently looking into SHEP, especially SHEP, and I did that Line too. Yes, we are experimenting with that.
Okay.
But so for now we don't have any results about that.
Because whatever complex your model is, you still can produce the linear regression with the lactose like so.
Yeah. Yeah, and also we are doing before that. I'd like to know our evaluate our decoding. So how efficient it is. Because if this is a good model, then I'm sure SHEP will show if there is some meaningful differences. But yeah, we are now creating descriptor statistics about the decoding phase 2 and trying to evaluate the loss functions and everything. Yeah, but after that, yeah, as I said, we are trying many interpretation methods.
Okay.
Yeah.
first question?
Yeah.
Engineering and attention layer.
So.
Do you think, have you tried without attention, then you used attention?
I'm not sure how.
So have you tried normal autoencoder without attention, then you feel like if we add attention, we
yeah.
What was your experiment?
An interesting thing about it, I remember plot without attention. So if I go back here and I'm still not sure about how to interpret that, but attention, it definitely focuses on some parts in the sensitivity analysis. But without attention, I checked that almost only the last two ones have any gradient on it. So with the sensitivity analysis, I think I found that yeah, these LSTMs maybe can't handle well enough this time series, so they need this attention to focus for one part. And yeah, understanding the decoding phase and understanding how efficient is the decoding and looking at without attention and with attention, I think that will give us an answer if attention is really useful and how useful it is.
This begs the question whether you are going towards transformers when there is nothing else than attention. So maybe you try transformers like work like.
No, I've experimented with transformers on another project, but for this I haven't got it on. But maybe that.
I mean, that's pure attention.
Yeah, and yeah.
See, that's one of the reasons. Yeah. Just one comment here. So, see, that's one reason why to present here, because we can collect some ideas from the audience. Okay, so
just my question is, if I'm understanding correctly, you just slap onto an autoencoder just for dimension reduction. So after the learning, you use the middle layer of that, and then the k-means on that.
Yeah. Yes, and our next step, I think, is this. Yeah, the towards k-means friendly spaces article, which basically initialize the clustering process with k-means, and after we found the k. Yes, after we initialized the cluster centers, then we can use the gradient-based method to further refine the clustering. So I think that that would be another huge step in the right direction.
any other questions? Yes.
Have you tried to interpolate the data between very various time frames? You can go to the data and have another new data. So if the patient is progressing from bullish to worse, then you may think that between checkups they have a linear or something like progression, and if you feel in the artificial data, you may have to compare or
Well, this would mean kind of a progression analysis for me. So yeah, we haven't tried this because because of the aim of the project. So basically, we try to work only with the raw data and try to custom it for now. So we haven't tried these methods.
How many of you were working on this project? And they just
3 with no report.
Not to forget to mention, we also have a medical
the data to understand the metrics.
Yeah, so basically on the tax side, really, but on the other.
It's cool.
Yeah.
Okay, any other questions? Okay, guys, we are in time, so thank you for your attention. and yeah, once again, I try to organize one meetup in November. If you have an idea who could present, then please also send me a private message. And yeah, so that's all. Thank you for Valer and Nori for your presentation, and Anta also for your presentation. And yeah, hopefully see you in November. And yeah, we will have some networking until 8:30, but around 8:30 please leave. So. Because there is someone who